Hello, Chemistry 30, and welcome to your lesson on redox titration. So if you loved predicting redox reactions and you loved titration stoichiometry from Chem 20, you are going to love this lesson. Our outcome for today is perform calculations to determine quantities of substances involved in redox titrations. So redox titrations are what how do I put this? Let me read that again. Redox stoichiometry in Chem 30 is limited to titrations. We're actually going to do some different type of redox stoic later on, so this isn't even completely a true statement. We're going to do cell stoic, which has to do with voltaic cells and electrolytic cells. You'll see that later, where we track electrons in a half reaction. But in this chapter, this is the only type of stoic we're doing. So redox titrations are actually really quite neat because they don't take an acid-base indicator to show the color change. They rely on the color changes of one of the chemicals itself. So OAs often used in redox titrations, there's two of them, and we'll talk about why. It's both actually because they're strong OAs, and then also because they have this really great color change you can look for to show the titration is done. So we use acidified permanganate ions quite a bit. So acidified permanganate, what I mean by that is I have MnO4 minus aqueous ion, and then I also have, of course, acid, H positive aqueous. We'll talk about this more, but we actually keep these two things separate. So the H positive is often in the Erlenmeyer flask, the sample, while I often use permanganate ion as the titrant, so that's in the burette. And then I also have acidified dichromate ions, so dichromate being Cr2O72 negative aqueous, and then of course it's acidified, so I have H positive there as well. Same exact thing, I keep the H positive in with the sample, while the dichromate is my titrant, so it is the burette. These change color when reduced, which we're going to actually take a look at the next slide. So for example, permanganate is pink-purple, while Mn2 positive at these concentrations are colorless. So here are the two reactions that I'm looking at, half reactions. I have this one, which is MnO4 minus aqueous plus 8H positive, gives us 5 electrons, and plus 5 electrons, sorry, gives us Mn2 positive aqueous and 4 waters. So here's kind of the ion side of things and the color change. If I take a look at MnO4 minus, this is the pink-purple color right here. So it starts out being a pink or purple, and then the Mn2 positive that it turns into once this has react, well, that's colorless essentially at the concentrations we're going to be looking at, which is normally very dilute. Okay, so this is colorless. Well, this right here is purple. And then if I take a look at the dichromate reaction, Cr2O72 minus, dichromate ion is orange or pale orange, while the chromium-3 right here is a green color. So I actually have this really neat color change for that one, where I go from orange to green, which is a very obvious color change to see. Okay, so here is a quick video actually showing a titration taking place. And I'll just kind of switch here. This is fine. So what I have is I have in the burette, the purple that you're seeing at the top, that's the permanganate ion in solution, and that's why it's the purple color. And then I actually have the sample that's being titrated. Let's say, for example, it's hydrogen peroxide. And then in here, I also have acid, H positive ion, right? So what happens is that when the permanganate goes in, it's supplied with the H positive, so now it can actually be an OA. It couldn't have been an OA until then. And then it does the redox reaction. Now, at some point, we're going to run out of Ra to react with. And then what will happen is the purple will remain. And that's about to happen right now. We're actually right at the end point with, I think, this drop. Yeah, so here we go. Now we've got a very, very pale pink. And what that pale pink represents is it represents permanganate that is unreacted and left over in solution. So if I take a look, I now have a little bit of this purple permanganate left over that didn't have any Ra to react with. So that's the end point, is when I have a little bit of purple actually remaining when it adds, because I don't have anything for it to react with. In the same way for dichromate, it would turn green instead of clear as it goes in. And then as soon as I get just a tiny bit of orange, meaning that I have unreacted dichromate, that would be your end point. So that's what you're looking for, is the point where you have a little bit of unreacted titrant that adds to the sample. So redox stoich is nearly identical to other stoichiometry, except that we have to build the redox reaction first using that four-step method we learned in a previous lesson before we can do the actual titration. So that means we need to list our major entities. We have to find the strongest OA, the strongest RA. We've got to combine it to make a net. And then at that time, we can actually start with the titration stoich itself. So these questions are long. They are very involved. And it's really easy, as we saw in my first version of this video, to make mistakes. And I'm going to try to actually do it this time where I don't make any mistakes, but it's tough because there's so many steps and you got to make sure that you're not zoning out like I did as you go through them. So first of all, let's take a look at this question and build our redox reaction first, and then we'll go to the math and try out the steps. So a solution of potassium permanganate. Well, actually, let's go to design. This is where the information is that we care about. So a solution of potassium permanganate. So I'm going to separate this into the two ions that I have that make it up. So I have K positive aqueous, and then I have MnO4 minus aqueous. Right, so to dissociate potassium permanganate into its two ions. Again, samples of acidic, so I have the acid in the sample, H positive aqueous, and then tin 2 chloride solution. So I have SN2 positive aqueous, and then I have as well chloride ion, so Cl minus aqueous. And then the last thing that I have that I haven't written down yet is I have water, H2O liquid. So what I have in terms of an OA is I've got MnO4 minus and I have H positive. So this is my SOA. And then I have tin 2, which is going to be turning into tin 4, I believe. So this is my SRA. And I should actually go through the process for figuring that out. I'm really skipping ahead here. Here's my MnO4 minus and 8H positive. So I would start from the very top left to find my SOA, and it would be right here. So this is what I'm looking at for the SOA. And then as I go from the bottom right, I'm looking for something I have. And the first thing that I actually find for that is the tin 2, which is right here. So this is going to be my oxidation, and this is my RA. So now I can write out my reduction and my oxidation, right? So I can do my half reactions. So for my reduction, I have MnO4 minus aqueous plus 8H positive aqueous plus 5 electrons. And just copying down this full half reaction gives me Mn2 positive aqueous and 4H2O liquid. So that's my reduction half reaction. And now I'm going to write out my oxidation, which if I go to this, I'm just writing this out backwards, right? Because this is a reduction going from left to right. So going from right to left, I have it losing electrons and it's an oxidation. So I have SN2 positive produces SN4 positive aqueous plus 2 electrons. So now I have 2 electrons down here, so I'm going to multiply that by 5, and I have 5 electrons right here, so I'm going to need to multiply that by 2, because 2 and 5 will meet up at 10. So I need to be very careful that I actually do carry through these multiplications to everything that's in these half reactions. I'm now going to change colors for my net. We're going to go to black, and let's now write this out as my net. So for my net, I have 2 MnO4 minus, so I need to make sure that I carry that 2 forward to everything in this half reaction. I have 16 H positive aqueous. I have 5 SN2 positive aqueous. Hopefully I won't run out of room here with my reaction. which gives me 2 Mn2 positive aqueous, 8 waters, and I have 5 SN4 positive aqueous. So that is my net reaction. I'm just going to double check and make sure I actually did do everything in terms of multiplying through, and it looks like I did. One way to double check all these questions, which is always a good idea whenever you write a redox reaction, is to compare your overall charge. So I have 2 negative, 16 positive, I'm at 14 positive, plus another 10. So I'm at 24 positive from this left-hand side. And then if I take a look here, I have 4 positive plus another 20, so I'm at 24 positive on the right-hand side. So this is even for charge, so I'm pretty confident that my net reaction is correct. Now, what I should have shown before, but I didn't, is the fact that this question has more data. I just kind of went over it with the bottom so that I could do the net on this page and then move it to the next. But this has right here all of the information that I need for the trials. So now that we have our net reaction, I can start writing down my knowns, my unknowns, my conversion factors, and I can start going through the math. So what I'm going to do now is I'm going to select all of this. I'm going to copy that over, and we're going to go to the next page where I can now paste this and start writing my knowns, my unknowns, and my conversion factors. So this is my starting point here. I've got my net reaction, and now I can move forward with this. All right, so I got my calculator here and I am good to go. So now let's write down the information that we have. So I've got this information here, titration of 10 mils of acidic SnCl2. So I know that I have a volume here of 10.00 milliliters. So I can write that down. And I know the concentration of this tin 2 as well. It's 0.0500 moles per liter. So I know that I can find moles for tin 2 from this information. And then if I take a look here at KMNO4, I can get a volume from this information. Now, really quickly, I can look at the trials 1, 2, 3, 4 and consider if I should get rid of one of them. And given that trial 1 is quite a bit far off of the other ones at 17.4 compared to 16.9, 16.7, and 16.8, I can confidently get rid of this trial. Also, if you look at the endpoint color, it's dark pink. So this is a trial where they definitely overshot the titration, the endpoint, because it ended up dark pink instead of a light pink. So we had a lot of unreacted permanganate. Too much titrant was added. So now that I have 16.9, 16.7, and 16.8, pretty obvious what the average volume is going to be for this, right? If I add those together, divided by 3, I know that my volume will end up being the middle value of 16.8 milliliters. So I'm going to skip ahead and just write that. What I'm looking for here is concentration of permanganate. So I'm looking for the C. So I'm now good to go to start on this problem. So I can do moles of SN2 positive aqueous is equal to concentration times volume. So I have 0.0500 moles per liter multiplied by 10.00 milliliters. So I'm going to work in millimoles here. So I'm going to keep the milli going. Liters is going to cancel out from here and from here. So I'll end up with 0.500 millimoles. And then for moles of permanganate, I'm going to use my molar ratio in order to figure out how many moles of permanganate I have. And that just comes directly from my coefficients. So I know that I have 0.500 millimoles of SN2 positive aqueous. And then if I look, I have 2 MnO4 minus and 5 SN2 positive. So for my molar ratio, it's always what I'm looking for, which in this case is permanganate, over what I have, which is SN2 positive. So I'm multiplying by 2, and then I'm dividing by 5. So this will give me an answer of 0.200 millimoles. And then finally, I can find my concentration of permanganate, so C of MnO4 minus aqueous, by doing moles divided by volume. C is equal to N over V. So I have 0.200 millimoles divided by my volume of permanganate, which I found to be an average of 16.8 milliliters, using the 3 trials that ended up giving us decent data. So 0.2 divided by 16.8 gives us an answer of 0.0119. And this is now in moles per liter. I got rid of the milli here because I had milliliters down below, so I'm now in moles per liter and I'm finished. So there we have a final answer of 0.0119 moles per liter. I always like to take a look at the concentration that I had here and compare it to here, and just make sure that it's within kind of the same realm, like within a factor of 10. And it looks good. We're good. So now I can move on to the next problem and tackle that one. So here, I have to find my trial data, but we're going to leave that for later on. Then we'll consider if we have to get rid of any of these trials. Let's begin by building our net reaction based on the information we have. So I'm actually going to move this up just a tad so that I've got some more space to work with here. So what is the concentration of chromium-2 ions in a solution obtained from the analysis of a stainless steel fork? So I have potassium permanganate titrated to oxidize 25 mils of chromium-2 to chromium-3 ions in an acidic solution. So I have, of course, K positive aqueous from the permanganate, potassium permanganate. I have MnO4 minus aqueous. I've got H positive aqueous because of the acidified. I've got chromium-2 ions that I'm titrating. And now this actually comes to an important point. I don't have chromium-3 when I'm building this net. Chromium-2 is being turned into chromium-3, but I don't actually have chromium-3 to start off. So I have this, and then I also have, of course, water, H2O liquid. So these are the major entities that I have available. So now I'm going to figure out what my OA and my RA is. But actually, this is really simple, and I feel like I don't even have to go to the screen. The SOA is the permanganate and hydrogen ion half reaction, of course. But for the chromium-2, it's telling me the half reaction right in the question. So I don't need to actually even go through this, right? I don't need to go through the process of finding the SRA. I know it's spontaneous, and I know it's chromium-2 turning into chromium-3. So the oxidation half reaction has been provided for me. So for my reduction, I have MnO4 minus aqueous plus 8H positive aqueous plus 5 electrons gives me, once again, Mn2 positive and 4 H2O liquid. And then for the oxidation, I have chromium-2, so Cr2 positive aqueous, reacting to make Cr3 positive aqueous and an electron. So that's my oxidation, and I have my reduction. So I'm going to take this, and I'm going to multiply it by 5, because I need the electrons to equal in both half reactions. So I have 5 here, 1 here, that will meet up at 5. So this is being multiplied by 1, which we don't have to show, but this one is getting multiplied by 5. So now I can write down my net half reaction. And I'm going to go to a different color for this, just so I can then copy and paste it into a different screen. So let's go with purple this time around. So we've got MnO4 minus aqueous plus 8H positive aqueous, so no multiplying needed there, plus 5 chromium-2 ions gives us Mn2 positive aqueous, 4 waters, and 5 chromium-3 ions. Okay, so now we're all good. I'm just going to double check my charge to make sure that I'm set with this. So 1 negative, 8 positive, I'm at 7 positive, plus 5 times 2 is 17 in total. While over here I have 2 positive plus 15 positive is 17. So that looks great, feels good. We are set to copy and paste this into the next slide where we're going to be doing the actual stoichiometry titration work. So here we go. I've got my net reaction. Now let's take a look at our data and consider how we're doing for the volumes, and then we can figure out our average. So if I take 14.2 and I minus 2.7, I'm going to get 11.5 from that. 25.4 minus 14.2 gives me 11.2. When I take 36.5, 25.4, I get 11.2 from that as well. And then finally for this one, I get only 11.1. So now when you take a look at this data, you might think, well, this is actually not that off, but actually in a titration, normally we want everything to be within like a tenth. So when we have 3/10 off, that's actually a pretty big difference. And I would say that this is not a good trial based on this data. I'll also mention that normally in a titration, it's hard with permanganate because permanganate shows up without a very visible meniscus. So you have to measure it from the top. But normally when we do titrations, we actually estimate our reading on the burette to the 100th. So really we should have one more decimal place for these values, but instead we're working just to the 10th. Don't love that with these questions, but it is what it is. So when I take a look at this data, 11.5 is far enough away that I think I'm better off not including it. So whenever you have a data point that is quite a ways off of the other ones, just get rid of it for that trial. It probably isn't a good one. So now when I take a look at volume, I am adding together 11.2 mils plus 11.2 mils plus 11.1 mils. And then I'm dividing all of this. Oh, let's try to do this line by 3. So that will give me 11 points. Don't know why I have an extra 1 there. Let's just erase that. Oh, yeah, perfect. So now what I have is 11.13 repeating milliliters, right? So that's my average volume. So that's what I'm going to be putting in for my potassium permanganate is volume is equal to 11.13 repeating milliliters. So now if I take a look at my other information, I'll just move this down for a second and then I'll move it back up. I have as well that I have 25 mils of the chromium-2 ion, so this volume will be equal to 25.0 milliliters. And then I also have a concentration for my potassium permanganate, so this time my titrant is my standard solution that I know. So I have 0.0114 moles per liter. All right. So now that I've got that concentration, that volume, and this volume here, what I'm looking for, the whole thing for this is trying to find the concentration of the chromium. So that is my unknown. I can now move this back up and let's try to meet that up just perfectly to where it was before. Hey, that's not too bad. We'll go right there. All right. So now I can find my moles of MnO4 minus, so N MnO4 minus aqueous is equal to C times V. So I have 0.0114 moles per liter multiplied by a volume of 11.13 milliliters. So that will equal, and we'll go ahead and plug this into my calculator here, 0.0114, 0.0114 multiplied by 11.13. And I end up with this in terms of millimoles, 0.12 0.6882. So let's go 0.127 millimoles, but we're going to keep that full answer in our calculator for going on to the next step. I'm actually going to pause this video and turn everything to black because I feel like the purple on a somewhat purplish background is not going to look very good. So I'm going to pause this, and then next time you see, it's going to be black. All right, hopefully that turns out better. So now we're going to go to moles of chromium 2. So N of Cr2 positive aqueous. I have my moles of permanganate, so I have 0.127 millimoles multiplied by, I have from my net reaction, 5 chromiums. Oh, actually, don't like how I showed that. I want to write down what that's for so I can show it canceling out. That's for permanganate ion specifically. So MnO4 minus aqueous. That is going to be 5 chromiums on the top. That's what I'm looking for over what I have, which is 1 permanganate, 1 MnO4 minus aqueous. So I have 5 over 1, which means that this is going to cancel out with this. So what I'm doing in my calculator is multiplying this by 5, and I end up with an answer equal to 0.634 millimoles. And now I can find my concentration of permanganate. So concentration of Cr2 positive aqueous is equal to moles divided by volume. So I have 0.634 millimoles divided by a volume of, at the end of the day, 25.0 milliliters. So I'm going to divide this by 25. And I end up with an answer of 0.0254. That is now in moles per liter, because my milli here cancels out with my milli here, so I have moles divided by liters. So 0.0254. If I compare this concentration to this one, once again, it is relatively close, within a factor of 10 for sure. It's almost within a factor of 2. So I feel pretty confident with this answer. So yeah, that's it. I'm good. Those are 2 examples. This example, straight from your workbook, it's question number 1. Should have mentioned that before I actually went through the solution. So you can go through it first and then check against this and see how it went, but it's not really any point in me saying it now because it's the end of the video and you've probably done what you've done. So maybe I add a little text thing during that point. All right, well, anyways, that's it for today. Have a good day.